Good day, everyone. Welcome to lecture 13 of the lecture series on microprocessor 8085. In this particular lecture, we will discuss about the stack and subroutine. So we will discuss what is a stack and what is a subroutine. Okay. So first job will be to discuss a stack. What is a stack? Okay. So after completing the stack, we will come to the subroutines. What is a subroutine? Fine. So let's discuss about a stack. What is a stack? Okay. So basically, stack in 8085 microprocessor, it is a memory okay, or we can say it is a read-write memory. Read-write memory. And this particular memory is a temporary memory. What I mean by temporary memory, so let's suppose we have this main memory. So this is our main memory. Okay. And now if I am writing a program for microprocessor 8085, so I am writing a program for 8085. So in this program, I reserve some memory from this main memory as a stack memory. Okay. So from the program itself, I reserve some space in the main memory, and that particular memory is the stack memory. Okay. So how will I reserve that particular memory? Basically, in this particular main memory, I take some address. Let's suppose this is the address 4F. I load this particular address in stack pointer. So stack pointer contains 4F. Okay. So that means my stack pointer is here, is pointing to this. So it by default means that I have initialized a stack pointer and I have reserved some memory in the main memory as a stack memory. And how I am going to use this particular memory? Now, if I have to store something in memory, I will store in the lower addresses, not in the higher addresses. Okay. So stack pointer is always initialized. It is a general practice to initialize stack pointer as some higher address and then store data at lower addresses. So that means, let's say I have stack, top of stack at, I have initialized stack at 60. Okay. So then I will store the data at the lower addresses. For example, at 59, location 59, location 58, location 57. I won't start at 61, 62. So my stack memory is from the lower side. So that is why it is also called that a general practice is stack grows downwards. Now somebody will say, why we are storing the stack at the lower memory addresses? Why not we are allowing it to grow upwards? So the reason is, so let's suppose I am initializing my stack pointer here. Okay. And then I am saying that my stack will grow upwards. Now at the up, let's suppose I have a user program here. User program stored in memory. So my stack will grow upwards, and it will grow into this user program, and it will result in errorless execution. Not only errorless execution, it will change the contents of the user program, or we can say it will start accessing illegal memories. However, in this particular case, when we are initializing stack pointer at some top location, then we are growing downwards. Now at the downward side, we are not storing any user program. We are storing at higher memory address. Now at the downwards, when it reaches to the end, for example, when it reaches to the 0, it cannot grow further. There we can say that stack is full. Okay, so it is not possible to access illegal memory locations in this particular scenario. That is why it is a general practice to keep stack at higher address and then store data at lower addresses. And this particular memory, stack memory, this particular memory, when we have initialized this memory inside a program, so how will we initialize stack memory? We load address in stack pointer, because stack pointer is a register. Okay, and we also know that memory address in 8085 is of how many bits? 16 bits. And stack pointer is also of 16 bits. So we have to load 16 bits into this 16-bit register. And for loading 16 bits, we know we have an instruction LXI. So we have already discussed this particular instruction. So we will write LXI, SP, and then address. Let's suppose address is like this, 40FF. It is in hexadecimal. Okay, so it is 16 bits. So I am loading this in the stack pointer. So I have initialized the stack pointer. So after initializing a stack pointer, so that means I have created a stack memory in my program. After initializing this, both the programmer as well as microprocessor can then use this particular memory, use this stack memory. So how will programmer use this stack memory? So programmer means how can we use this stack memory in our program? Programmer can use this stack memory by putting data into a memory, putting data into this stack memory, and also getting data out. Data. How will it put data into the memory, and how will we get data out of this stack memory? We will discuss the instructions for this. Okay. And how will microprocessor use the stack memory? So microprocessor also uses stack memory to store the return address in case of function call. So microprocessor automatically stores the return address of a program into a stack memory whenever it calls a function. And this particular part, how we store the return address, how microprocessor automatically stores return address onto the stack, this part will be discussed in the second part of this particular lecture, where we will be discussing about the subroutines. Okay. So first job is how the programmer uses this stack memory. Okay. That is the first part that we have to discuss. Fine. So let's discuss how our programmer can use this stack memory. Okay. Or we can say what are the different instructions that can be used to access this stack memory. Okay. So we will discuss the instructions to access stack memory. By the program, or how we can access stack memory inside a program. So as I said, whenever I have to use stack in my program, the first job is initialize initialize stack pointer. Okay. And for initializing stack pointer, that means load 16-bit memory address into stack pointer. So how will we load it? LXI stack pointer and then memory address. Let's say memory address is 4000. 4000 in hexadecimal. Okay. 4000 in hexadecimal. The second part is put data onto the stack. So when we have initialized a stack pointer, then if I need to put some data onto the stack, or we can say store data onto the stack, that particular operation is also called a push operation. Push operation. Okay. So in microprocessor 8085, push operation always stores 2 bytes of data. So you have to remember, it always stores 2 bytes of data. Okay. So always, it is the case that is followed everywhere in microprocessor 8085. Push operation always stores 2 bytes of data onto the stack. So how it does? It first decrements stack pointer. Okay. The first job is the push operation. What is push operation doing? It decrements stack pointer, stores 1 byte. Okay. Again, decrement stack pointer, because we know that at one memory location, we can only store 1 byte. So since stack pointer is pointing to a memory location, so that means at that particular location, we will store only 1 byte. Then we will again decrement stack pointer and then again store 2nd byte. Store 2nd. So this is what is happening inside a push operation. First, we are decrementing a stack pointer, then we are storing 1 byte of data. And this push operation, since we said that it saves how many bytes? 2 bytes. So that means this push operation can only store data that is stored in register pairs. So that means it can push data from register pairs. So what are the possible register pair? One register pair is BC. Okay. And the second register pair is D and E. And the third register pair is H and L. So these are the register pairs that it can store onto the stack. Also, another pair is PSW. So what is PSW? So this is also called program status word. Okay. And this PSW is combination of accumulator plus flag register. So flag register is also of how many bits? Flag register is of 8 bits and accumulator is of 8 bits. So we can store program status word onto the stack. Okay. And you have to remember, let's suppose, and what is the instruction for this particular operation? The instruction is push. Then I can push. What are the possible values? B, C, D, E, H, L, and PSW. The instruction is push B. So if I am writing push B, or I can write push D, or I can write push H, or I can write push PSW. So these are the 4 instructions that I can push data onto the stack. So when I am doing push B, okay, so what we have stored in stack pointer initially, what was there in stack pointer? In stack pointer, we were having 4,000. Okay, so let's suppose this is my memory. This is the main memory, and let's say this is address 4,000. Okay, let's write other addresses as well. What will be the lower address? 3F, decrementing 1. 3FF, then it will be 3FFE. Again, this will be, let me write on this side, 3FFB. Again, 3FFC. Okay, so let me write it out. Now I am doing push B. Let's suppose B register stores 50 in hexadecimal, and C register stores 32 in hexadecimal. Okay. Let's say I am doing push B. So what it is doing? So what I said that push operation is doing, it decrements stack pointer. So what was stack pointer? It was 4000H. So it will decrement it. What will be a stack pointer now? Now stack pointer will be 3F. Okay, so this is the value of stack pointer. Then what it is going? Store 1 byte. Now which byte will it store? Will it store B byte or C byte? Or we can say the byte stored in B register or the byte stored in C register. It always stores the higher byte first. Higher byte will be B. So it will first store B. Okay, so what is there in B? 50. So it will store 50 here. Then again, it decrements stack pointer. Now stack pointer will be 3FFE. And after decrementing stack pointer, it stores second byte at that location where the stack pointer is pointing. Where is stack pointer pointing? This particular location. So what is the second byte? The second byte is it will store C. Okay. So now we will store this register value in this location. So what we are going to store? 32H. Okay. And this is where my stack pointer is pointing. Now let's suppose if I am doing push DE. So what I will do? Push DE. So I will decrement stack pointer. Then store higher address byte. So what will be the higher byte? D. Then again decrement stack pointer and store the lower byte. So what is the lower byte? E. So here for push H, I will first store H, then I will store L. For PSW, program status word, I will first store accumulator register and then I will store flag register. So these are the operations related to putting data onto the stack. Okay. So now we have to discuss how we can take out data from the stack. So the third point is get data out from the stack. So getting data out from the stack is also called pop operation. So we can get data out from the stack. Now let's suppose I have to get data from the stack. So let's say I have to get data. Now, if I am getting data out from the stack, I have to store that data in some location, in something. So if I am getting something out, I have to then receive that data in something. So I will receive that data in my registers. And also when I am doing pop operation, I will always pop 2 bytes of data together. How many bytes? 2 bytes. And I will store these 2 bytes in a register. So what are the possible instructions? One will be pop B, another will be pop D, another will be pop H, and the last one will be pop PSW. Okay. So what is the pop operation doing? So let me explain it. What is pop operation doing? It will first, what it is going to do, it will first get byte pointed by stack pointer. So let's suppose my stack pointer is pointing here at this location. So it will get data from this location. Okay. So what is the data? 32H. And place, okay, get data, get byte pointed by stack pointer and store in lower register. So in a register pair, we know that there are 2 registers. For example, B has 2 registers, B and C. So lower register will be C, higher register will be B. So it will store in lower register. Then after that, increment stack pointer. Okay. Then after that, get second byte and store in higher register pair, higher register. Okay. And then again, increment stack pointer. Okay. So this is the pop operation. Let me explain it here again. So pop operation, what it is doing, it also has 4 operations. The first is get byte pointed by stack pointer and store in lower register. Okay. The second is increment stack pointer. The third is get byte pointed by stack pointer and store in higher register. And fourth is increment stack pointer. Okay. So in B and C, B is higher register, C is lower register. Okay. And in PSW, A is higher register and flag is lower register. Okay. So this was about pop, and let me repeat push again here. Push is first is decrement stack pointer. Second is put lower register byte at location pointed by stack pointer. Okay. And third is again decrement stack pointer. Fourth is push higher register byte at location pointed by stack pointer. So you can see that in a complete operation, pop operation, in a complete pop operation, stack pointer is incremented by 2 because it is incremented 2 times. And in a complete push operation, stack pointer is decremented by 2. Also, you can see from here that the data is accessed into the stack via a stack pointer. So we can get data only that particular byte which is pointed by a stack pointer. Okay. Also, from these operations, you can see that we can access this stack memory. We can access stack memory via stack pointer in first in, last out order. So that means the data that has been put last will be the first data that will be popped out. We cannot take the data in between. We can only take data that is stored at the lowermost address, or we can say the data that has been most recently put into the cache. Okay. So the stack is accessed in via stack pointer, and we can get the data in first in, last out order only. Okay. So this was all about the stack and how we can access the stack. Okay. Now, after this, we will discuss about the subroutines, or yes, we will discuss about the subroutines, and we will see how we can use stack memory in implementing subroutines. So let's now discuss what is a subroutine and how stack memory is used in subroutines. Subroutines. So what is a subroutine? So let me write it here. So basically, subroutine, it is a group of instructions that are used to perform some operation. Okay. So let me give an example. For example, let's say I have to write a program. So let me write an algorithm here. So the program is, let's take the example of a traffic light. Okay. So in the traffic light, let's say I have to use the following. For example, I have to turn red light, let's say, and then delay for 10 seconds, then turn yellow, delay for 5 seconds, turn green, delay for 3 seconds. Let's say, for example, this is my program. Okay. So you can see that in this program, one operation is repeated continuously. What is the operation? Delay operation. So delay operation is to be done repeatedly. So if I write a program, so in the program, first I have to write instructions to turn red light. Then I have to write instructions to delay, instructions for delay. Okay. Then instructions to turn yellow, and here it is repeat, then repeat. Repeat means go here. So instruction is to turn yellow. Instruction is for delay. So instruction is to turn green light, and then instruction is for delay. So you can see here that for delay, I have to write these instructions repeatedly. Okay. So yes, here we have a delay of 10 seconds. Here we have a delay of 5 seconds. Here we have a delay of 3 seconds. Yes, there are some internal details that may vary, but the instructions will be same. So here instruction is for delay, I have to write instruction is for delay and instruction is for delay. So this type of operation is repeated again and again. So instead of writing these instructions for delay again and again in my main program, so this is my main program, what I am going to do, I will create a separate program, or we can say separate set of instructions. Let's say I have these instructions for delay here. Okay, and I will give a label to these instructions. Let's say I will give a label delay. You can give label anything, any name. Then we have these colon and then instructions for delay. Now in the main program, let's say this is my main program. So I will give a label main to this main program. You can give any other label, but since it is a main program, let's give it a main label. In the main label, I will write instructions for instructions to turn red light. Okay, then we have instructions for delay. So we will execute these instructions. Basically, we want that this set of instructions should be executed. So this set of instructions that are used to perform some operation. So what type of operation they are used? To perform delay operation. This is called a subroutine. Okay. So what we are going to do here, we will call subroutine, this particular subroutine. Okay. Then calling subroutine means it will execute these instructions. Okay. And after completing these instructions, we will go back to the main program. That is, from this subroutine, we have to return to main program. So that means at the end of subroutine, we should have an instruction to return to a main program. So now let's suppose this is at address 1. This is at this instruction is at address 2. Then we have to return at instruction 3. So what is the instruction 3? So this one, instruction is to turn Y. Now again, we have to use instructions for delay. Instead of writing instructions for delay, we have written it separately here. We will call subroutine delay. So its name is delay. So here also we will call it by its name, delay. Okay. So it will call delay. Then again, it will go back and we will have instructions to turn green. Then again, call delay. And at the end, we will have halt. Halt means end of the main program. So you can see that subroutine is a group of instructions that are written separately from the main program. And these instructions are used to perform some specific operation. And whenever I have written a subroutine, this subroutine will be used only when we call this subroutine from the main program. So I will write some important steps here. First, subroutine is written separate to main program, separate to main section of the program. Second, A subroutine runs only when it is called. And the third is, at the end of subroutine, there is a return instruction that goes back to instruction after the call. Call means when we have called something. Okay, so let me write it again here. So what is there in the subroutine? We have to write subroutine. Second is we have to call subroutine. And third is we have to return from subroutine. Okay, so let me write it in greater detail. So let's say this is our main program. So let me write a label. Label is only used to we can say in an assembly program, it only shows at what point we are. Or we can say instead of directly writing the address, we write the label. So let's suppose this is at address 1000. Then we have instruction 1, let's say. Then we have second instruction 2. Let's say it is at address 1001H. So this value depends upon the type of instruction. If it is a 1 address instruction, 2 address instruction, or 3 address instruction. Then let's say we have a call delay. It is at 1002H. This is the address. Okay. Then we have, let's suppose, instruction 3. So I will show that this call is a 3 address instruction. So I3 will be 1005H. So I will repeat it. We will explain this call instruction, why it is a 3-byte instruction. So it is 1005H, I3. Then we have, let's suppose, halt. Okay. Now my delay is here. Delay. Let's suppose it has instruction 1, instruction 2, and let's say this address is 1010H. This is 1011H. This, and then we have return. Return is 1012H. Return instruction. Okay. So this is my subroutine. This is subroutine performing some function. So let's say what is happening inside this program. Okay, so this is my memory. And you have to remember, whenever we are using a subroutine, we have to use a stack. So we have to use a stack. I will show you why we have to use a stack. So that means I am saying here we have to use a stack. But whenever we have to use a stack, we have to, what we have to do? We have to initialize a stack pointer. So let's say I am initializing a stack pointer. So stack pointer is 4000H. So here in the main program, since I am using call subroutines, so I will initialize subroutine somewhere here. So for initializing, I will write LXI SP 4000. So my stack pointer contains 4000. Okay, so let me write this program. So let's say it is here. This instruction is here. So let's say this is instead of 1000, this is 9F and 1000H is LXI SP4. Basically, this is also a 3-byte instruction. Let's simplify it. Let's say its address is 1000H. Okay. So SP is 4000. Let's start from here, from the main program. What is initially there in program counter? In program counter, we have 9F. Okay. So you have to remember this is a 3-byte instruction. So if it is 1000, next one will be 1003. This will be 1004. This will be 1007. Okay. This is 1008. PC is 9. So it is executing this instruction, I1. Okay. Now when PC gets incremented, so it is a 1-byte instruction. I1 is a 1-byte instruction. So the next value in PC will be 1000H. So that means it will execute which instruction? This instruction. So in SP, we will have 4000H. Now our PC will be 1003H because this is a 3-byte instruction. Now it will execute this I2. Okay. So it will execute this instruction. Now PC will be 1004. Okay. Program counter will be 1004. Now here, what is the instruction? The instruction is call delay. Basically, it is call. Call means go to this location. What is this location? 1010H. Okay. So it is not delay. Actually, the call instruction is like this. Call and then address. This is address. However, in our program, instead of writing an address, we write a label. Why we are writing a label? Because when we are loading this program into the memory, we don't know the actual location where we are loading. So during the compilation itself, it will change this label with the actual address. Our compiler, or we can say the assembler, will change this particular label with this particular address. So call instruction is actually like this: call and then address. Address is of how many bytes? 2 bytes. So basically this is the starting address of subroutine. Okay, starting address of subroutine. So it is 2 bytes and this is 1 byte. So it is a 3-byte instruction. Okay, now it is calling here. So what it is going to do, it will update this particular PC with this call address where it is going. So the new value in PC will be 1010H. And also this call will store the next address. What is the next address after the call? It was 1007H. It will store this 1007H onto the stack. So this address 1007H, this is also called a return address. What is the meaning of return address? Return address means that when I return from this subroutine, I have to start from this particular address. Okay, and it will store this particular address onto the stack. So that means it is doing push operation. Okay, and it is pushing this particular value onto the stack. So how many bytes it is pushing? It is pushing 2 bytes. And we have already discussed whenever there is a push operation, we will push 2 bytes onto the stack memory, and we also decrement stack pointer by how many times we have to decrement it by? 2 times. So let's suppose this is 4000, it will be 3FFH, and this one will be 3FFE. So it will store 1007H here. So here 10 will be stored, higher order byte, and here 07 will be stored. Now my stack pointer is here. Because whenever we are doing push, we will first decrement. Decrement means go here, then store the higher byte. Again decrement, store the lower byte. Okay. Now what is there in PC? In PC we have 1010H. So it will go here. So that means it will execute this instruction, I1. Okay. So it will execute this. PC will be updated 1011H. Okay. So now it will execute this I2. Now PC will be updated 1012H. Now what is the instruction at this address, at this program counter? So instruction is return. So what is return instruction doing? Return instruction is automatically pop 2 bytes from stack and put in PC. Okay. So this is the functionality of a return instruction. So return instruction is putting these 2 bytes. So what we have stored onto a stack, we have stored the return address. So it will take these 2 bytes and will store in PC. So what will be the new value in PC? 1007H. So that means now program will start from this particular location. So what will be the new? And also popping 2 bytes means that we have to increment our stack pointer. So the new value in stack pointer will be 4000H. Previously, when we did the call operation, stack pointer automatically becomes 3FFEH. Now, again, using a return instruction, stack pointer becomes 4000H. Then it will execute this instruction, then this instruction, and the program ends. Okay. So you have seen here that using this call and return instructions, they are automatically using a stack. Okay, so let me repeat on the next page. So what is call doing? So call instruction is like this: call, then address. So what is the functionality of this? So it will, so this particular instruction, internally what it is doing? Internally, it will put this address in program counter and the address of next instruction. So next instruction. And it will do push address of next instruction onto stack. So it is doing it internally, call instruction. Then we have return. What is return instruction doing? Pop address from, or we can say return address from stack and put in program counter. So that is the function of return instruction. So you can see that implementing subroutines. So if we have to implement subroutines, we have to do two things. So what we have to do, we have to first initialize stack pointer, then use call and return instructions to use the subroutine. Use the subroutine. So everyone here may have already discussed about the programming language. For example, somebody has known about the Python or C programming language. You know that in those programming language, we have function calls. We call a function and we return from the function. So this call and return is also used to implement functions. Okay, so call and return are used to implement functions, higher level concept of functions. Okay, also you know that in function calls we are doing parameter passing. Parameter passing. Okay, we are passing parameters from the main program to the another function. For example, if I am calling some function, let's say the name of function is add, then we are using parentheses and writing parameters here. Now, if in this particular scenario also, in the subroutines also, I have to pass the parameters. How will I pass the parameters? So how we are passing the parameters in subroutine is that is done using the registers. So let's say I have to tell my subroutine that you have to use this particular value. What I am going to do in the main program, I will put that value into the register B. Okay, in register B. Then in my subroutine, I can use this register B to get that particular value. So we can do the parameter passing using the registers. So here we can do parameter passing via registers. Okay. So this particular thing completes our discussion about the subroutines. So what are subroutines and how we can use the subroutines. Okay. Now there are some special subroutines, or we can say special call and return instructions. Okay. So we will discuss about those things here. So now we have to discuss some special things. What we have to discuss about restart instructions. So these are basically the subroutines, or we can say the call instructions. We have to also discuss about the conditional call. So what is the meaning of conditional call? Up to this point, we have discussed about the unconditional call. Unconditional call means we are not checking any condition to perform call function, or we can say to execute call instruction. Condition call means that we will execute a call instruction, but based on some condition. Okay. So what are the conditions? Conditions are checking the flags. Checking the 4 flags. So what are the flags? Basically, we have 5 flags, but we are checking only 4 flags. One is carry, another is 0 flag, another is parity flag, another is sign flag. So based on these flags, we will decide whether we have to use a call instruction or we don't have to perform the call instruction. Conditional call and conditional return. So we will discuss these things, these instructions. So it will be a brief discussion, but let's discuss it here. Okay. So first of all, let's take the restart instructions. So in our microprocessor 8085, there are 8 restart instructions. There are 8 restart instructions. So all 8 restart instructions are 1 byte instructions. Okay. So what are the instructions? The first instruction is RST0. It is written like this, RST0. Another is RST1. Another is RST2. Another is RST3. Likewise, we have RST7. These are 8 instructions. Okay. So all these 8 instructions are basically call instructions. Okay. So when we are writing RST0, what it is doing, it is calling this particular location. So that means in the PC, it will put 0000H. What is there at that particular address? We don't care. Okay. We will see that what is at that particular address and why we are using these restart instructions. Likewise, we have RST1, it is calling 0008H. RST2, it is calling, so there is a difference of, how much difference? It is the difference of 8, 0010H. Likewise, the others at the end, it is calling, RST7 is call 0038. Okay. So internally it is like this, but the restart instructions are written like this: RST0, RST1, RST2, RST3. We only remember what it is doing. What is the functionality? Why we are using these restart instructions? We will discuss this in the case of interrupts. These instructions are using in interrupts. So when we are discussing about the lecture in which we will discuss about the interrupts, we will discuss the functionality of these restart instructions. Okay, so basically restart instructions are also call instructions, or we can say these are kind of function calls, or we can say RST0 is a subroutine. Okay, and what type of subroutine? It is running a subroutine stored at this particular memory address. Likewise, RST1 is a subroutine that is stored at this particular memory address. And what is that subroutine doing? We will check that when we are discussing the interrupts chapter. Okay, fine. So this completes the discussion about the restart instructions. Now let's discuss about the conditional call and conditional return. Okay, so let me rub this portion here. So what is conditional call and what is conditional return? Let's first take the conditional call. So basically, previously we were doing call, let's suppose F A A H. So what was this call doing? It was simply putting in PC F A A A. So that means it was going to this particular address and it was running instructions stored at this particular address. And at the end, we will have return. Return means that it will go to the next instruction after the call. Okay. So this was unconditional call, means we were not checking anything. Now there are conditional calls. Conditional calls means that we have a call instruction. Call instructions that are getting executed after checking a condition, after checking some condition. Checking some condition means it is checking the flags, these flags. Okay. So let me write some of the instructions. For example, one instruction, I will write all the conditional call instructions. One is CC address. So what is this instruction doing? It is a call instruction. It is saying call if carry flag is set. So that means C is equal to 1. So this instruction, if we have an instruction like this in our program, so it will say that I will go to this particular address only if carry flag is set. However, if carry flag is 0, it won't execute this instruction. It will directly go to the next instruction. Okay, fine. So if we have an instruction like this, call address, then we have, let's suppose, I1 after this. And at this particular address, we have stored instruction I2. Okay, so it is going here. The program will come here. It will first check the carry flag. If the carry flag is set, if that is equal to 1, then it will go here. It will start executing from this point. Then here we will have return. Return means that it will go back here. However, if the carry flag is 0, it won't go here at this particular location. It will directly go to the next instruction and will continue like this. So here you can see that we are checking a flag, and based on that flag, we are deciding whether we should make a call or we should not make a call. So this is one instruction. Another is CNZ, another CNZ and then address, subroutine address. Another is CZ. Oh, sorry, this is CNC, CZ address, CNZ address, CM address, CP address, CPE address, and CPO address. So what is this? This is a conditional call CNC. This is call if carry flag is reset. So that means carry flag is 0. Okay. This is call if zero flag is set. Okay. This is call if 0 flag is reset. So this is call if sign flag is set. So this is call minus if sign flag is set. Set means result is minus. So CP means call positive if sign flag is reset. Okay. Call P even. This is for the parity if parity bit is set. And this is call parity odd if parity is odd, is reset. Okay. So these are the conditional call instructions. Likewise, we have conditional return instructions. So I won't be explaining them in detail. For example, one is RC. So it is saying return if carry flag is set. So that means go back, return back only if carry flag is set. If the carry flag is not set, don't return, go to the next instruction after this return. Okay. Likewise, we have RNC and other instructions. So how many these conditional call is 1, 2, 3, 4, 5, 6, 7, 8. For 4 flags, we have 8 conditional calls. Likewise, for 4 flags, we have 8 conditional returns. Okay. So this is about a conditional call and conditional return instructions. Okay. Now the last point related to this particular lecture is nesting. So I won't explain this in detail, but you have to remember what is a nesting. Nesting means when one subroutine calls another subroutine. Okay. So let's say this is my main program. It is, let's suppose it is doing call delay. Okay. Whatever there is after this. Then we have delay. This is my delay subroutine. And let's suppose it has instruction 1 and then it is calling another subroutine delay 1. Okay. And here I have delay 1. And it has this instruction. So see what will happen in the stack. So let's suppose this is my stack pointer initially here. At the end of this delay, we will have return. At the end of this delay, we will have return. Let's suppose this is address 1000. And after this, this next address is 1003. Okay. This is address 2000. The next is 2001. Okay. And after this, we have 2004. This is my return. Okay. So let's suppose this is 3000. Now let's see what will happen. So let's say my stack pointer is here initially. So it is doing call delay. So it is going here. So we know that call instruction stores this address onto the stack. So it will store 1003 here. And my stack pointer will be here. So let's say this was the initial stack pointer. My stack pointer is here. So now it is calling here delay. So it will execute this. It will do a call. Again, call is there. So when we have a call, we know that we are storing a return address onto a stack. Now it will store this particular address onto the stack 2004. Now my stack pointer will be here. Because stack pointer gets decremented by 2. Then it will execute this. From here, it will go here. Now it is executing this. Here it is return. Return means that pop the value from the stack. So in the PC, we will pop these 2 bits. What will be 0, 4. Now pop means these 2 are out. My stack pointer is here. Now, okay. Now PC contains 2004. What is 2004? Here, this particular delay. It will execute instruction is here. Again, we have return here. Return means that again pop from the stack. Now PC will contain 1003H, and this is decrementing by 2. So that means my stack pointer will come here. Now PC has 1003. 1003 was this location. So from here, I will execute the instructions. So this is how nesting is applied in our programmers for microprocessor 8085. So how many nesting we can do? That means how many calls we can do. Call from one subroutine to another subroutine. We can do depending upon the number of locations in stack. So if we are continuously doing the call, our stack will become full. Then after that, we won't be able to push more data onto the stack, or we can say we won't be able to perform more call operations. Okay, so that is also one of the disadvantage of recursion. Recursion means when a function is calling itself repeatedly. Okay, it will lead to stack full. Okay, stack will get full. So the number of nesting is limited by the number of locations in the stack. Okay, so this completes our discussion about the stacks, how these stacks are used, what are the different instructions that are there that are related to the stacks. Okay, and we also discussed how we can use this stack to implement subroutines. Okay, and how call and return instructions are using the stack. We also discussed how we can pass parameters from one function call to another function call via registers. We also discussed about the conditional calls, conditional returns, and also a procedure called the nesting. Okay. From the next lecture, we will discuss some of the programs that will use these particular, we can say, components of microprocessor 8085. It will use the delay, or we can say counters. We will use the calls. We will use the nesting. We will use the return. We will use these different types of components in our programs, and we will understand how they are useful in implementing programs for microprocessor 8085. So let's meet in the next lecture. Till then, goodbye.